So if you've done it in ALEKS already, you've basically seen the same style questioning and whatnot that we're going to do here. All right, so take a minute, try the problem. That's another question I was asking. All right. So this one's a ton of calculations. So one of the cool things about Desmos is it can actually allow you to do all these crazy calculations. So, and believe it or not, everything I'm going to show, I'm showing you, you could technically do all this on a TI calculator as well. So it's nothing special about Desmos that does it. It's just easier because it's on a computer to do it. So we want to find our slope. So what's the equation for slope? So we're going to set this point as x1, y1. So right now I have my equation as that's minus 6 over minus 3. Correct? Okay. The x, they're giving me right there. So I'm going to set that as x. How would you find the y? Yeah. You're going to plug the x right into that equation, right? So I'm just going to put that equation right here. Now, you're all like, okay, that's a crazy looking slope formula. You're absolutely right. But it still only has one variable. It's still just x. Because in essence, that's f of x. That's y. The reason we do that is because I can now put that right in a Desmos. So now on this list here, I can literally do 2.9, 2.99, 2.999, 3, 3.01, 3.001. How's it? Hold on. 3.1, 3.2. Oh, I forgot the negative side. I'm like, why is this not coming out nice? That's why. I forgot the negative sign. There we go. And I think I forgot 2.8. So now we have all our values. To fill in that chart. That's a little easier to do the calculations than plugging all the numbers in one at a time. An interesting conversation with one of my students today, and they're like, they were in one of their engineering classes, and they're like, the teacher just says they were doing like a massive system of equations problem, and like the teacher's like, when I do this at work, I just plug it into the computer and it gives me the answer. I don't sit there and do it out all by hand. I'm like, yeah, that's the difference between an engineering class and a math class. Math class, we expect you to do that, which I think is kind of stupid. Like, none of you are doing this out by hand when you leave here. You're all going to use a computer to do this stuff. Nobody does this stuff out by hand. So I would rather teach you how to use those things to actually do it and still understand the concepts behind the thing. So calculations are nice, but it's really easy to make mistakes when you're doing like 20 calculations for one problem. All right, so we're looking for the slope. Does everybody understand why we're doing these points? We're basically getting closer and closer to that. So we're basically creating those secant lines through that. And as we get closer and closer to that point, where 3 minus 3 on the bottom will give you 0, we can find the limit as it gets closer and closer to that point. That is x2. That is y2, because that's f of x. How would you find y2? You would plug x2 into the problem, right? So all that right there is what the equation is. That's f of x. So they are the same x, but the one on top is actually doing a calculation to find that y value that I would plug in. Because if I was going to plug in 2.8, down the bottom would be 2.8 minus 3. And then I would plug the 2.8 into this problem to get the y and plug it into that spot right there. And then do the calculation. So by writing out the equation this way, I already have all that done. It's like as I'm using the actual equation to do the work for me instead of manually putting the numbers in place while you're doing it. You could still do it the other way. It would be totally fine. You'd get the exact same answers as long as you don't make a mistake. And even this, you have to be careful. When I first did it on this one, I forgot the negative sign when I typed it in. And I'm like, something's not working out right because I know what the answer should be, and it was coming up with something crazy. I realized I missed the minus sign. So it's even this, you can still make a mistake. The key piece is like, and I'll show you what happened. Leave my thing. There we go. So when I forgot the negative sign, the answers didn't seem to make sense. I was going to negative infinity basically and positive infinity. It wasn't getting closer to a number. So that's the thing. When you're looking at doing your work, even when you're doing ALEKS or when you're doing your test or anything else like that, it's if you make a mistake, you want to figure out ways to notice that mistake to figure out where you need to go back and fix things. So it's like, I knew those answers didn't make sense. Something was wrong. I went back and realized I just didn't have the minus sign there. Put the minus sign. Now the answers make sense. So if you're going through and doing the calculations out for this, even if you're doing them out by hand, and you get some crazy number in here for 2.99, but all the other numbers make sense, odds are you messed up somewhere in your calculation for 2.99. Go fix it. Yeah.
We take the actual test. For problems like this where we're using Desmos,
You're still going to have to fill out the numbers in the problem.
Right.
So You could just say I use Desmos to do the calculations. That's fine. I don't need to see all your work out.
Okay.
Yeah, I don't need, so I would expect you're gonna do some kind of thing like this on your paper, so you can write down what you wrote in the problem, and you're still gonna have to fill out all the boxes for it. So that alone is gonna show me you've done some kind of calculations or figure out some way to get those numbers in there to figure that part out. So that's fine. Also, the more work you show me, the better chance of if you get something wrong, I have points to give you. So that's always to be in the back of your mind. Show me as much work as you possibly can. So if you screw up and get the wrong answer, I can give you points. So, all right. So what is the apparent slope for the tangent line? It's 3. So the limit goes to 3. Good. It's basically the same problem. That's okay. We're gonna go after that. It's basically the exact same problem. All right, this one. So in this one, they're giving you this crazy graph and asking you for some limits. In this case, they're only asking for the limit as it goes to 2. So what is the limit as it goes to 2 from the right? Because it's the little plus sign there. So that's this one right here, right? So that would be -2. As we're coming from the left, that's that, which goes to 0. And does the limit exist at 2? No. Let's do 0. All right, what about 0? The limit goes to 0 from the right. It's going to 2. Limit goes to 0 from the left. 2. What's the limit as x goes to 0? 2. It is not 4. F of 0 is 4. Okay. Is these are both discontinuities. Is the discontinuity at 2 removable or non-removable? How?
Which part?
This one.
Oh, it's a jump constant.
That is a jump discontinuity. So because it is a jump discontinuity, there's a break, complete break in it. You cannot remove it. It is non-removable. What about the discontinuity at 0? Yes, that is removable because technically that answer could have been there.
The one at 4, would that be removable? Or would that be a jump?
The 4 would also be a jump because there's a break there. So the difference is on a jump discontinuity, there's nothing that I can put in place to eliminate that gap. Okay, because in a removable discontinuity, I would say that f of so I would have said that f of 0 is 2. I would have made that answer correct. Okay, as the piecewise function, even though right now it's -4, I would have said it was 2. that would have removed that gap. That's why that's removable. So your jump discontinuities and your infinite discontinuities are not removable if it looks like that, where the point goes through a specific spot. So basically, if the limit exists, then it's removable. Because if you notice, like these two, the limits do not exist. So if the limit exists, I can remove the discontinuity. All right. Similar problem. There's a little bit difference to it. But what is the limit as x goes to -1 from the left side? That would be 3. That's this. What about from the right side? That's going to infinity. And what about the limit as it just goes to -1? Does not exist. Remember, those two limits have to be the same for the whole limit to exist. And this would be another non-removable discontinuity. All right, another limit one. This one has the equations and not the graph. So take a minute, solve this one out. Find me my 3 answers. Kind of equate, well, it says it. This is a piecewise function. So the limit as x goes to 3 from the left, which equation am I using? First or the second? First, because it's x is less than 3. So I've got 3 over 2 minus 3. So that's -3. Yeah. What about x equals 3 from the right? First or second equation? Second equation. Now, as crazy as this is going to sound, if I change those to 4s, it'd both be the second equation. So don't always make the assumption you're doing one equation to the other equation. Actually look at the domain restrictions and make sure that it's actually the spot where it is breaking and using both. So I have 3 minus 1 squared minus 6. So 4 minus 6 is -2. All right, so what's the limit as x goes to 3? This one does not exist. And that would be a non-removable discontinuity. If I change that to 7, if I change that to 7, they both would have been -3, and the limit would have been -3. And the way this one's set up, it actually doesn't equal at negative, it doesn't equal at 3. There's no equal sign there. So I would have had to write another equation there to make it a removable discontinuity. But since they both connect, we could remove that discontinuity by putting a point there. Or we could have just moved it by just making one of them equal. That would have also removed the discontinuity. All right, find me my limit. What's the first thing you should always do? Plug it in. Does it work? No. Okay, so we've got to solve this one out somehow. How are we solving this one out? Yeah, we can. We're going to factor, right? We're going to factor the top. The top is the difference of squares. So the top is t minus 4, t plus 4 over t minus 4. So we can cancel out the t minus 4s. So we're left with t plus 4 going to 4, which means this goes to 8. Yeah. That's the same one. I've noticed this. Let's do. Hold on. Real quick. I make up a problem real quick. Really? Okay. Yes, I'm forcing you to really practice that factoring. And if you plug it in, does it work? So somehow we've got to, but if you plug it in, because this is actually very important, when you plug it in, so we've got 12 minus 2 minus 10, you get the 0 over 0. Remember, if it comes up to 0 over 0, that means you can factor it out. Okay? So you can factor, or just because I've been doing it half the day with my pre-calc students in class, you actually could do synthetic division because you know 2 works. You know 2 gives you a 0. So you could actually use synthetic division. 2, 3, -1, -10. And that gives you 3x plus 5. So when you cancel out the top and the bottom, you would get 3x plus 5. So, or you could factor. So we're looking for 2 numbers that multiply to 30 and added -1. So minus 6x minus 5x minus 10. Here it is, plus 5x. Thank you. I'd have caught that right here.
I know you.
Yeah, I would have caught it right as I did this one. Like, wait, my sign's wrong. So we still get the same breakdown. So they both work. They both come up. We cancel up the x minus 2, and you're going to get the 3x plus 5. So just different ways to go about getting the same answer. And then we plug back in the 2 to this, and you get 11. So the limit is going to 11. Any questions with this one? All right. All right. What about this one? Well, 3 over 0 is 0. What's cosine of 0? 1. This right here becomes sine of pi over 2. What's sine of pi over 2? That's also 1. So my answer is negative 1 over 1 or negative 1. Going through as many problems as I've gone through in the trig functions, they all seem to work out to basically pi over 2, 0, or 3 pi over 2. They all seem to work out to the 4 main points. So, and those are the 1, 0, 0, 1, negative 1, 0, 0, negative 1. So you won't need your whole unit circle. You won't need, so like I wouldn't worry about memorizing that part of the unit circle, at least for now. You will need it for later on for things, but at least for now, you don't need to do that. I also seen the vast majority of these seem to work out right when you plug the number into them too, which kind of makes life easier. All right. Intermediate value theorem. So remember the intermediate value theorem? 3 pieces that you have to show. The first one is that it's continuous over that interval. The second one is that the values exist and one is greater than the other one. So one is on one side of 0, one's on the other side of 0, and they're greater than one's greater than the other one. And then based on that, can you actually apply the intermediate value theorem? So first and most important piece is this function continuous over the interval negative 9 to 1? Why? I know it doesn't ask you why here, but I want to know why. Yeah.
It's not continuous because there's value probably would be 0 within the range of the interval. That would make it so the function
Doesn't work. It's not continuous at that point. All right. So first off, it's not a polynomial, right? This is a rational function. If it was a polynomial, it's automatically continuous. So because you don't have any of the domain restrictions. This is a rational function. We're dividing by x. So if x was 0, so x cannot equal 0 because I would be dividing by 0. And 0 is between negative 9 and 1. So it is not continuous because the rational function is not defined for at least one value in that set. Because of that, we actually can instantly answer the final question. No, we cannot apply the intermediate value theorem because it is not continuous. But let's go through and do the other parts of this one just to see how the rest of them work. So what was it? 2. Okay, so I can choose it out. So plug in the negative 9 and the 1. It's not equal. -9 is greater than 0, and 1 is less than 0. So the other pieces that cannot be equal to each other, because if they're equal to each other, then they don't technically have to cross anywhere. 1 has to be greater than 0, 1 has to be less than 0 for it to work. So the other two criteria work. So it works there and works there, but it wasn't continuous. So therefore, the final answer is nothing. We can't use the intermediate values there. Does that make sense? So again, we use, believe it or not, every single calculator, when you try to estimate a 0, when you ask it for a 0, it is actually doing this exact thing, just with very close numbers to determine where it actually crosses the x-axis. So it's actually doing the calculations back and forth to determine where it crossed the x-axis based on the intermediate value theorem. So if this theorem didn't exist or didn't work, we would not be able to find zeros on our calculators. All right. Next one. Find me the limit of this one. Your major.
Liberal arts and sciences.
What do you want to do?
Sure. Something like STEM now, like something involved with like people and like interactive stuff, considered education.
Okay.
Considered something.
I'm just trying to find a project that would match your, like, what you want to do, so it's worthwhile to you, more than just a random. See if I can do something with music. I always forget that the pen. All right, what's sine of -3π/2? Why is it 1? So yeah, -3π/2 is basically the same as π/2, which is 1. So I've got -3π/8. That's my final answer. All right, one more trig problem. Promise this is the last of the trig problems. All right, what's the sign answer? So negative 2 pi over 4, which is negative pi over 2, right? So sine of negative pi over 2 is negative 1. Because it's the same as 3 pi over 2. Or 270 degrees. All right, what's tangent of negative pi over 4? Yes. So remember, the pi over 4, so tangent is sine over cosine. And the pi over 4 is where tangent or sine and cosine are the exact same. So tangent of pi over 4 will always either be 1 or negative 1. And since this is going backwards, it's the negative 1 version. So I've got negative pi over 2 minus 3, which is negative 1. So my answer is pi. All right, asymptotes. Shift over. So what I would do for this one, and you could do this out by hand, and the other ones, the last two we're going to do it by hand, but for the middle two, it's actually easier to look at it as a graph. instead of plugging in a bunch of numbers. So for 1, hold on a second. X to the third minus x squared. X squared plus 3x minus 4. Okay. Never mind. You can do this one up by hand. Actually, really easily. So I take that back.
We come across this question, we're gonna think it's like one left, negative 4 on the left, still gonna end up with a negative 2 or.
Not necessarily. That's actually what I assumed, which was a wrong assumption. Because then I graphed it and I'm like, wait, that's not where those problems are. Well, not all, both of them. One of them is. So you can actually factor this one. So we can take out an x squared on the top and we're left with x minus 1. The bottom, we have x minus 1 and x plus 4. So you can actually cross out that. And then you could actually plug in the 1. So plug in the 1, you end up getting 1/5. So the limit for x equals 1 is 1/5. Now, I noticed that after I graphed it. And I looked at 1, I'm like, wait, there's no asymptote here. So I'm like, wait, that means I can actually factor it in. Because remember, the first thing I always said is plug the numbers in and try it. Like, you never know what you can find. And if you plugged it in, you would have gotten 0 over 0, which means you could have factored that piece out. That also makes my problem a little bit simpler when I'm doing the negative 4 one. Because if we look at that, this bottom part, if we're going from the left, this bottom part is going to be negative, and the top part is going to be positive. So by factoring it, it made my life a little bit easier to notice that number. Since the bottom's negative and the top is going to be positive, that means this is going to negative infinity. So that would be from the left. If we were going from the right, this part right there would end up being positive because the 4 is always going to be bigger than that number. And the top's still going to be positive because it's squared. So we would have gone to positive infinity. Also, by factoring it, these two problems are identical except for the removable discontinuity. So that means my end behavior, or when it's going out to x goes to infinity or x goes to negative infinity, we can use the simpler equation to work with it. I don't need to do the more complicated equation to do that part. So you can either do, for this one, pre-calc brain works. It's not an overly complicated, doesn't have the square roots or anything else in it to make your life a little harder. So what do we know about the end behavior for this problem? Or the, as we go from x goes to infinity, what's going to happen? It's going to go to infinity. So now the question is which one? So as we're going to positive infinity, the top's getting infinitely large, right? In a positive direction because it's squared. and the bottom is going to be positive, so this is going to go to positive infinity. As we're going to negative infinity, so that's the x goes to infinity. As we're going to negative infinity, the top is still going to be positive, but the bottom's going negative, right?
To change your streets and stuff.
Oh, yeah, that would help. There we go. As I'm writing this. So the top goes to positive for that one. And as this is getting larger, it's still being positive, so it's going to positive infinity. As we're doing the negative version, x squared is still going to be positive. The bottom is going to more negative, so it's going to be negative there, which means it's going to go to negative infinity. Any questions with those? Okay. Next part of this question. What are the vertical and horizontal asymptotes? I have no horizontal asymptotes. Goes to infinity. And my only vertical asymptote is x equals negative 4. So I have one vertical asymptote and no horizontal asymptote. Any questions with that one?
How did you get the, for x, is -4 to that?
So we're really looking at, because I know it's going to go to infinity. So we're really looking at determining if it's going to a positive infinity or negative infinity, right? So really all I care about is sign. So I know my x squared is always going to make, no matter what number I plug in there, it's always going to be positive. Because squared by definition is going to be positive. So then we're looking down here at this part here. Go away. We're looking at that part there. So I'm coming from the left. So all my numbers are going to be greater than like -4, -5, things like that, right? So all those numbers are going to be bigger than that +4. So that answer is always going to be negative. So I know that's going to be negative. So since it's a positive or a negative, I get a negative infinity. So a lot of times when you're looking at these, like once you know it's going to infinity, all we care about is sign. So don't sit there and you don't have to do a million calculations. We're literally just looking at what's happening with the sign. I know the top positive, I know the bottom's going to be negative. And that's what I was saying. If we went the other direction, if we were coming from the right, that x is always going to be less than that 4 is going to be. So therefore, the 4 would have always been bigger. So it would have been positive or positive. Give me a positive. This one's a really simple question. What's the limit as x goes to infinity? What's the limit as x goes to negative infinity? 2. That's it. Hey, I got to do softball every so often, right? That's the same thing. All right, this one.
all the ones that have, excellent. Are those because there's, if it's infinity, it's so close to zero, there's never near zero?
Yes, so the rule states, as you get infinitely close, as the denominator gets infinitely large, the fraction goes to zero. That's that theorem that we looked at on, I don't know if I did that last week or the last one or the day before. It was last test. It was last lesson, the one I did on Tuesday. Been a million things the past 2 days. Like I'm trying to remember which day it was. Yeah, that was Tuesday. Yeah, anything 1 over x to any exponent will always go, the limit of that always goes to zero. That's why this rule and the way we do it works. If that wasn't true, none of this would work. You do have to do this out. You can't just assume just because like this one goes to negative infinity, not positive infinity. So it's like because of that -2 down the bottom. So, and this one just goes to zero. That's your test. So everybody make sure to bring your computer. If your computer dies really easily, bring a charger. I have plugs for you. If you just want to charge it on the state's dime, bring your charger, charge the computer. You will be allowed to use Desmos. You have until the day of the test to finish module 2 in Alex. So you have till next Tuesday to finish that up. It will then force you to module 3 come Wednesday. Okay. So you will be able to go back and fill in stuff in module 2 after down the line, but it will lock that module to move on until you finish module 3. The other thing that I noticed as I was just looking, there is still a handful plus of you that have not put in your new code. For most of you, this expires like the day of the test. So if you have not gotten your Alex code yet, I would highly suggest doing that this weekend and put that in. Otherwise, your access is going to lock and you won't be able to finish any of the other work. So, or do the test because it's going to lock on you. So make sure you get your access codes taken care of. There's nothing I can do to extend it any further, unfortunately. It only does 14 days.
This practice test is on Alex too,
Yep, the
right?
practice test is already on Alex. You can do it. It's called Chapter 2 Review Test. So you can do it as many times as you'd like. Yes.
At the beginning of class, I didn't hear what you had said. You said something about the notes.
Yes. So I'm going to allow you to bring in a note card this one because I already told you, and you guys, most people were already starting to write them. After this point, you